Today I will create an analog clock with shaders, and welcome to this unexpected video because I was free today and there was nothing much to do. Alright, now I'm on a website called ShaderToy and I'm going to use it to create that analog clock. So first let me just increase the text size so we can see better, and let's get rid of this. And I will basically go, let's just visualize our UV. So you can see that I have UV 00 here and 11 here. Now I don't have the actual UVs. I'm calculating it by going frag coordinate divided by the resolution. Now this frag coordinate is actual coordinate of this screen, so it will be 00 here up to 1800 and then 1013 here. Okay, now what I want is I want the origin 00 at the middle, so I can go frag coordinate and subtract half of my resolution, so 0.5 into I resolution.xy, and then I will divide I resolution.y to compensate for the aspect ratio. So now my UV's y will go from 0.5 to negative 0.5, but this x could go beyond minus 0.5 and 0.5. All right, now I have this UV, and from this, let's create a dial of our clock. So for that, I'll just probably create a new function which will return float dial, and it will take vector 2 point, which will be our UV, and a float radius, so R. And for now, I'm just going to be declare dial equals 0, and let's return dial. Let's call in our function, so dial of UV, and let's say 0.48. So I have the all black screen because dial just returns 0 for now. Now here I want to create a line segment, and for that, once again, I'll create another function. So float line, and this will again take our point, which will be our UV, then the first point of our line and another endpoint of our line, and once more float for the thickness of the line. I'll call it size. Now here first I want a vector to PA. So basically I want vector that points from point P to point A. So for that I can go A minus P. And to get the direction vector, you just basically go destination minus source. Okay, so PA. Then I want another vector BA. So I want vector that points from point B to point A. So I can again go A minus B. Then I'll create a float H or step. And I'm going to go dot product of PA and BA divide by square length of BA. So I can simply go dot product of BA. So this is basically Pythagoras without the square root. So it is c square equals a square plus b square. Okay, and now this dot product can go between -1 and 1, and this dot product will be positive because it's basically the squared length or magnitude. But this thing can go from -1 to 1, so I'll just clamp it to go from 0 to 1. Then I can get the distance, closest distance from the line. So float d for distance equals length of PA minus BA into H. Okay, then I'll just return B. And if you don't know who this guy is, then you are probably missing out. So just type in this name in your search engine, okay? Now, on contrary to popular belief, I cannot explain the like theorems or the actual calculation why we need to do this, but I can show you what this function is doing using Desmos. So what line function does is, imagine that I have this line segment AB that goes from -1 to 1, and I have this point P on -0.5 and 1. So the line function will give me the nearest distance from this point to my line segment, like this one. So I would get this distance. Now imagine that if my point P is here, then I will get this distance. And if this point P is around here somewhere, then I would get this distance. So this is the gist of that line function I've just created. All right, now let's call our line function so we can see what it does. So I'll go style equals line and pass in P. Then I want line starting from 0, 0, and I need vertical line, so I'll set point B as 0 and point, basically this R, and let's pass in the thickness, so 0.02, and right now this thickness won't do anything, but let's just see. So basically I have a distance field, or the distance from my line segment to the current pixels. Okay, now let's actually cut out a nice line segment from this. So for that I can use smooth steps, so I'll go smooth step of d minus size, and let's go edge 1 to 0.0001 or 0.001, edge 2.0, and this. Now let's see. So here I'll get this nice line segment. Okay, now it's very big, so let's just go 0.002 and 0.005. Okay, this is nice. Okay, now I want this line to be the marker for 12 o'clock, so here I'll simply go R minus 0.08. Yeah, that's too wide, so 0.05. Yeah, this will do. Then I can simply go plus equal to this, so I would have the same line segment on top of that, but before I do that, I can rotate my point so that I would have this line segment at around 1 o'clock position. Okay, so for that I need to create a rotation matrix. So for that, let's create a new method that will return matrix 2 by 2. Let's call it rotate. It will take degrees. Okay, then I need to convert this degrees into radians. So for that I'll go float pi equals 3.1415, and float angle equals degrees multiply pi divide by 180, because, well, pi radians is 180 degrees. Okay, so then I'll just return a new 2 by 2 matrix, so mat2. So this is what the rotation matrix will look like. It goes like cosine of angle minus sine of angle, sine of angle, and cosine of angle. Now in GLSL and HLSL, matrices are in column major order, so I need to go vec2 of cosine of angle and sine of angle and vec2 of minus sine of angle, cosine of angle. So this will be my first column and this will be my second column. Okay, then in the dial function I'll rotate the UVs or points, so I'll go P equals rotate of, and the 1 o'clock position will be 30 degrees away from the 12 o'clock, so I'll go 30 into P, and so I'll have this. Then for 2 o'clock position I can just simply copy paste this, but first I want this line segment to be thinner, so I'll go 3, and also want it to be a little bit shorter, so 0, 1. Yeah, this looks nice. And I'll just copy paste this, so I'll have 2 o'clock position, and then once again I'll copy paste this, but here I'll just use the size for my first dial. So I'll have the 3 o'clock position to be like the 12 o'clock position line segment. Okay, all right, we have this first quadrant of our dial. Now you could of course go plus equals this 8 more times to have the entire dial, but the thing is my UV's X goes positive in this direction and negative in this direction, so I can reflect this part around here by simply going P dot X equals absolute of P dot X. So I have this part reflected over this. Similarly, I can reflect this part here by going absolute of Y. So I can simply go P equals absolute of P, and I have the entire dial. Pretty cool. All right, this feels a little bit empty, so let's include minutes or second markers as well. So for that, I should probably create a loop. So for int I equals 0, and this quadrant will total have 16 markers. So I less than 16, I plus plus. And here I'll simply go dial plus equals line, and then each marker will be, so in the entire dial I would have 60 markers or 60 line segments. So and the entire dial will be 360 degrees, so each marker will be 6 degrees away. Yep, so I'll simply go 6 here, and let's just comment this. I don't need this. Comment this. Okay, so here I'll have 60 line markers. Now I only want the 12 o'clock, 6 o'clock, 3 o'clock, and 9 o'clock to be more bold, so I need to include an if condition. So I'll go if I equals 0 or I equals 15, only then do this. For the rest, I'll go, whoa, I'll go this. There are two thick, so let's also make it thinner. -2, and let's go 1. Okay, so this looks nice. And for 1 o'clock and 2 o'clock, I need a slightly bigger indicators. So here I'll go another else if. Here for the 1 o'clock, I would have I equal 1, 2, 3, 4, and here will be the 1 o'clock marker. So I equal 5, and or I equal 10. Then I need this. It's okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, so our dial now looks pretty nice. Okay, let's collapse this. All right, now let's create our second hand. So I'll go float SS hand equals line segment of my UV, and I want the vertical line basically, so I'll go vec2 of 0, and let's start it from minus 0 minus 0.08. Then I'll go vec2 of 0, and I want to go up to 0.4. And let's set the size, so it would be 0.002 maybe. All right, so I have the second hand. Now let's add it on top of the col plus equals ss hand. So now I have second hand, and let's make it red. So vec2 of 1.1.1. Sorry, vec3. Okay, now I have second hand, and now I can rotate it based on the seconds. So first I'll go float t equals I time, and I time will give me the seconds of the simulation. So this seconds I will receive it, and let's calculate the rotation. So float angle equals, I would go t, and here instead of passing UV, I'll go rotate angle multiply UV. So now you can see that my second hand is rotating. Now it's basically rotating, it's basically going 35 degrees angle at 30. So at 40 seconds, I'm rotating 40 degrees, which is not accurate, probably, because in 60 seconds, this second hand should rotate 360 degrees. So for every second, it needs to rotate 6 degrees, right? So I'll go multiply 6. And let's check. So now it's kind of accurate, because at around 50 seconds, the second hand is pointing at this 10 o'clock position. So the rotation is nice, but it is rotating continuously. I don't really like that. I want it to go from like in this top motion way. So for that, I can use floor function, and floor function will give me the integer part of the number. So let's say I have 70.65, so floor will give me 70. All right, so let's just recompile. So now it's going like this, which is nice. Okay, we have second hand. Let's do minute hand. So I'll go float hand equals line of rotate angle into V, and I'll go vec2 of 0, and I'll start it with 0.06, let's say, and end it at 0 and 0.35, let's say, and the size will be a little bit bigger, so 0.004, and I need to, for now, I'm going to set the angle to 0. And let's add the second hand, so col plus equals minute hand, I should say. So here I'll have this minute hand. Now let's calculate the angle for that as well. So I'll go angle. So the minute hand will rotate 6 degrees when the second hand will go, basically when second hand will complete the entire 360 degrees revolution, our minute hand will move 6 degrees. So for that I can go second hand rotation into 6 divided by 360, and I can simplify it. So 6 ones are 6 and 6 60s are 360, so I can simply write divide by 60, and here you can omit the floor function, but I'm just going to write, and let's go. So, and basically we cannot see it, so I'll just fast forward my simulation time. So yes, the minute hand will also rotate nicely. Now let's do one more hour hands. For that, I'm again going to go angle equals 0 for now. Float HH hand. This is a weird name. Rotate angle into UV. I need it to start from minus 0.04, let's say, and vec2 of 0 and 0.28, and the size will be a little bit bigger, so 0.005. And let's add it. So col plus equals HH hand, and I'll go, let's calculate the angle. So this is my minute hand rotation, and we know that when the minute hand will complete the 360 degree rotation, our hour hand will move 30 degrees. So I'll go multiply 30 divided by 360, and of course I can simplify it. So zeros got cancelled, 3 ones are 3, and 3 12s are 36. So I can simply write divide by 12. Then you can again omit the floor function here, but I'm going to write it anyway. And let's recompile. So yes, let's fast forward the time way more. So we can see that the rotations are nice. and accurate. Okay, let's slow down a bit. Alrighty. Now let's say I want this second hand on top, so I can simply go call multiply equals 1 minus s's hand. So this line will cut out my second hand pixel which overlaps on here, so I will have simply black values where this second hand should be, like this. Okay, then I will add it on top of it, so I would have second hand on top. Right now there's no way I can grab the system time in ShaderToy, so let's define it. Float HH equals, let's say 1. Float equals, let's say 30, and float ss equals, let's say 10. All right, so this is our second hand rotation, and let's add on top, so ss, and we know that for every second the second hand should move 6 degrees, so multiply 6 once more, and I can probably make brackets here. So yes, I have stopped the simulation, so for 10 seconds my second hand should be here. Then let's do that for the minutes. I'll go plus and again for every minute the minute hand will rotate 6 degrees. Yes, that's accurate, and let's do that for our hand as well, so plus HH, and for every hour our hand will move 30 degrees, so 30. So now this is accurate, and it will work for like 24-hour format as well. If I go 13, it wouldn't change anything, so that's all cool. Alrighty, now I don't really like this flat minute and hour hand, so let's try to shape them a bit. Okay, so here 0.004, I'll go float size, and we'll pass in size here. Okay, so okay, let's take this out, and I'll go rect to SD equals a rotated UV, and pass in ST here. Now let's say for if there is no rotation, our ST's Y will be negative here and positive here, so I can simply go size equals absolute of st dot y. So here I would have 0, then it will go positive in both direction, and if I just flip it around, go 1 minus absolute, so I would have 1 at the origin, and it will decrease as we move away, and that can go negative, so I'll just clamp it. 0 and 1. Alrighty. Then I need to shape it, so I'll go size equals power of size, and 15, let's say. And power function will simply bring the values that are closer to 0 more closer. Or basically it will just darken the values which are less than 1 as we increase the power. And then I'll multiply it with 0.004. And let's visualize it. Clamp. All right, 1 point. And let's rotate the minute hand so we can see better. Okay, it got way more. It's a 0.4, so my minute hand will look like this. Okay, now let me play around with the size. 3.2. Yeah, 0.2 looks nice. Okay, then again we'll do the same thing. So st equals basically this. And size equals clamp of 1 minus absolute of st dot y 0 1 size equals power of size, and let's go 10 this time. Multiply 0.015. Let's pass in the size here. So yeah, this looks nice as well. Let's turn on the simulation, and it's way fast. Let's go real time. So okay, let's just decrease this minute hour hand is to 2 and minute hand to 3. Okay, that looks nice. Now we know that there are 24 hours in a day, and I want my time to go. I want to complete my clock's 24-hour in the 24-hour real time, so that would be the real time scale, okay? Because this will simply evaluate to 1. Now let's say I want to complete my 24-hour in 1 hour. I can go like this. So in 1 hour my clock will complete 24 hours. Now obviously I can't show you because you won't stick around if I just let the simulation run for 1 hour. So let's just stop and reset it. So we have 12:30 start time, and let's say I want my 24 hours to finish in 30 seconds. Okay, now this is seconds and this is hours, so I need to convert this to seconds, which I can simply go by multiplying 3600. Okay, let's compile, and so in 15 seconds I would have my clock to complete the 12 hours, and we'll be back to 12:30. Okay, let's check. Okay, it's spinning pretty fast. Okay. Whoops. So at around 15 seconds, my clock have completed the 12 hours. Okay, so that's how you can control your simulation time. Okay, now I wanted to match the real time, so I'm going to remove that, and let's just play. And yep, it looks pretty nice in my opinion. And I think it's about time I ask you to hit that like button, and if you're new here, consider subscribing for more shader videos like this. Yep, that's it from me, and I'll see you in the next one.